Hello! So in these notes so far, our focus has been to learn that definite integrals we should think of as net accumulation that can be positive or negative. So definite integrals can be positive or negative. And then our other focus here is highlighted in the middle, that area is always positive. So even though definite integrals can be negative, if we're looking for the area, sometimes we as humans are going to have to intervene to make that definite integral positive to find what the actual area is. So this video is going to take those ideas and we're going to look at some examples. So let's start with example 5. Here I have a piecewise function and I am supposed to write and evaluate an integral expression that gives area of the region under the curve. So in order to do this, I'm going to need to draw my graph. Okay, so we're going to start off by graphing this function. So -1 is my transition point, and I see that the graph is just stuck at, it's going to go, I don't know. I'm looking at it from -3 to 3, so I'll just include all those points. Okay, so I see that the left function is just at 3. So I'm just going to draw a straight line here at 3, like that. And then on the right, I have this line, which has a slope of -1, and it goes through 2, is the y-intercept. So I see this goes up here and fills in that hole, and then there and there. I mean, it's not perfect. Something like that. Cool. So I'm supposed to find the area of this region. One thing that I'm noticing is that I have some positive area right here. So anything above the x-axis will count as positive area. But I also have some of that negative. Well, area is not negative, but I see that the definite integral is going to be negative there. Okay, so I'm going to have to split my integrals up to be the positive area as well as the negative area. Okay, so I want purple. I like the purple. Okay, so my integral, if I split it up between the positive and negative, one integral will go from -3 to 2, because that's where it changes from positive to negative. And I'll just write of f of x dx. And then I'm going to subtract the definite integral from 2 to 3 of f of x dx. And the reason why I'm subtracting it is because since this is negative, I want to turn it positive, so I use that negative sign. So the area under the curve, so the area of this green function, sometimes you're going to have to kind of split it up to make it geometric shapes that you know. So I see a rectangle there, and I see a triangle. So this green area is just the area of a rectangle and an area of a triangle. Okay. So the area of the rectangle I see has a base of 2 and a height of 3. So that's 2 times 3. And then plus the area of the triangle. The triangle has a height of 3 and a base of 2. So the area of or is that 2? No, sorry, that's 1, 2, 3. I almost made a mistake. It's okay if I do that. Okay, so the area of a triangle is 1/2 base times height. So here is the positive integral, the green one. And then I need to subtract off what I'm going to get in that little red integral, which is another triangle. So I see it has a base of 1 and then 1. So these y values are the reason why they turn negative. So we're going to give our y values a sign if it's negative. So this triangle is 1/2 the base times the height, which is a negative height, I guess, because it goes down. So here we end up with 6 plus 9/2, and then I'm going to get a double negative, which becomes plus, which is what I wanted all along, right? We didn't want to subtract the area because area is always positive. So I wanted to add it. And this is another half. So I get 6 plus 10 halves, which is 6 plus 5 is 11. Did I make a mistake? I made a mistake. This is not the same as my notes. Maybe I'm fine. Maybe I messed up in my notes. Okay, let me know in the discussion board, or let me know if I made a mistake. I'll give you an extra point if you're the first one. Cool. Let's look at these examples in the back. We're going to skip to example 7. Okay, so let's say I have this function f. So this curve here is f of x. And from my curve, I can see that from -4 to -1, I get this A1, area 1. And then from -1 to 4, I get this area 2. So we are just going to practice determining whether values will be positive or whether values will be negative. Alright? So I see from -4 to -1, it's asking me what that area is. I can just straight up say, oh, that's area 1. Okay? Easy, right? And then now it's saying go from -1 to +4. So -1 to 4, I get A2. Since definite integrals can be negative, I'm going to say this area is -A2. Okay? Because definite integrals are can be negative. And that one is because it's below the x-axis. Alright, so in C they kind of try to trick us. So in C the integral goes from 4 to -1, which means I'm going from 4 to -1. I'm going in reverse. So we talked about in the last video when we go in reverse, it will become negative whatever it is. So it's negative A2, which is positive. So that one becomes positive because we went in reverse. So D, the integral from -4 to 4. So now I'm doing the whole thing. So that means I'm going to have positive A1, and then as I keep going, it's going to be minus this A2. So it's like I'm combining parts A and B into C. Okay. All right. Then I can see right here in E, we have the same thing as in D. So I know this first part is A1 minus A2. And then over here, there's a lot going on. So this is the same. I can just multiply times whatever is in this integral. I can see this is the same as what I have up there. So I can substitute in negative A2. So this becomes A1 minus A2 plus 2A2, which will end up being A1 plus A2. So that's kind of how we can manipulate the areas. Okay. Let's flip the page. There's a couple more examples. So in this example, we have another interesting graph. I noticed that it specifies it's composed of 3 line segments and a semicircle. That is just to make really clear that these are geometric shapes that you are able to take the area of. So it's really specifying this is just a semicircle. You know the area of a circle, or you should know the area of a circle. And so we can find these areas no problem. Part A is just kind of a little challenge problem to help us find what this x-intercept is. You all should be able to do that, but I don't really want to spend time doing that. So I will let you know this x-intercept is 4.5, okay? You should be able to find that if you are a super stellar student and want to challenge yourself. go ahead and confirm that you are able to determine that. It's 4.5. Anyway, so let's skip to these integrals though. Okay, I'm going to do b with you, and then I want you to try c on your own. So pay attention as I explain b. So b is this integral here, and I'm going to kind of highlight the areas. So it's -7 to 0, which includes this value right there, which will be a negative definite integral, and then it also includes right here, which will be a positive definite integral. Okay. So this isn't telling me it wants me to find the area. It's saying just evaluate the definite integral. And so I don't need to necessarily make the negative definite integral positive, because it's not asking for area, it's just saying solve this definite integral. I will, however, use the property where I kind of split them up into two. So I'm going to split it up from -7 to this point right here, -2, -7 to -2 of f of x dx, and I'm going to add it with -2 to 0 of f of x dx. And I'm just splitting those up because I can see I have one triangle right there, and then I have a quarter circle, and so I want to find those areas separately. For the triangle, I see that I have a base of, what is this base? 1, 2, 3, 4, 5, and then I have a height of -1. So the area of the triangle is 1/2 base times height. And then for the quarter circle, I see that this quarter circle has a radius of 2, so r equals 2. And so a quarter circle is a fourth, a quarter. Pi r is 2 squared. So I'm using pi r squared as the area and multiplying it times a fourth because it's just a quarter of the circle. So here I get -5/2, and then over here I end up with just pi. And that is my definite integral. I want you to try c on your own using what we just did. I will help you a little bit by kind of highlighting the areas that you need to find. So you need to find that positive one, and then this negative definite integral. And when you do that, so do all the work, when you do that, you should end up with 7/2. So you can check your work with that. Okay. I want to get you started on example 9. That's another one I want you to try on your own. I know this equation looks nuts. It's actually kind of a really cool graph. So I'll show you the graph. And again, those of you who are really trying to figure stuff out, you can kind of figure out how I came up with this graph. So I see it goes from -2 to 3. So I'll go from -2 to 3. And this graph, it's nuts. It looks like this. So it's just that -1 and 1. It goes open circle like that, open circle like that. So if you're bold, figure out how I made that graph, and then you should evaluate that definite integral using your areas. So again, I'll give you a little help. Oh, I'm helping you too much. This is going to be so obvious now. Well, whatever. So we're finding those areas to solve our definite integral. So show me that work. I'll leave that one as a mystery. You have to tell me what this is in the discussion board. So let me know what that answer is. Okay. So those are all the examples of kind of looking at area, how we can find area from definite integrals, and the fact that definite integrals can be negative, but area cannot.